Hello, everyone. Welcome to today's show. Another exciting episode with some exciting guests, and we've got a surprise here. Robert, what is that?
It's a turkey head, turkey hat. Yeah, happy Thanksgiving, everyone. For those of you in the I guess Western Hemisphere, those of you celebrating Thanksgiving, I know everyone doesn't, but if you are, happy Thanksgiving, Alessandro. Everyone else, happy Thanksgiving. Yeah. We're glad to join you on this special occasion.
Yeah,
and
happy Thanksgiving.
Festive. Yeah.
Yeah, no, thank you all for joining us today. We've got an exciting show. So today it's Innovation Coffee ML inside ML compilers using open source TVM with OctoML. And we're going to have some special guests. But before diving into the show, as usual, Robert, do you want to give us a recap of what we did last week?
Sure, absolutely. Last week was another exciting episode of Innovation Coffee. We got to speak with Pamela Cortez and Jen Fox from Microsoft, who walked us through Azure IoT. It was so much fun because, not only did we get to just tangent off on a bunch of kind of random topics in that area, but we also got to see some cool demos. Each of them shared some cool demos with us. We talked about the makerspace, and then so many resources were discussed. I mean, Alessandro, I feel like last week was one of those days where there were just so many different resources that were shared. And Alessandro so kindly took all of these resources and updated the description of last week's video. So if you did miss it, have an extra hour. As I always say, go check it out. Go watch last week's episode, and then you will get access to a whole bunch of resources in the description. Don't forget to like and subscribe. Thank you, Alessandro. Back to you.
Cool. No, I mean, I completely agree. It was a really fun episode. We actually went for an hour and 20 minutes. I mean, not to put you off, but it was a lot of really interesting chat. And actually, we had an opportunity to really talk about a lot of different topics with our guests. And we, at the end of the show, if you remember, we brought in another special guest host that we have with us sometimes. And we actually have the opportunity to have him with us again. So welcome, Karl, to the show. Hi, Karl.
Hello.
Welcome again. Happy Thanksgiving to you.
Yeah, thank you. Yeah. After this, I'm going to start by eating way too much food.
I wish, you're making me want to be in the US. I'm not in the US, so, I'm not going to eat a lot of food, but, it would be awesome to be there and be with you guys. But maybe next year.
Yeah, next year.
We could do a live one
next
together.
Year. Yeah.
Karl, I think we brought you in this show a couple of times, but I'm not sure you've actually had a chance to introduce yourself properly to the audience. So I would, if you want to do that today, I think that's a good opportunity.
Yeah, I can definitely do that. So yeah, I work with these two, obviously. And right now I am currently the only machine learning evangelist at ARM. Haha. But yeah, so that's exciting. I've been working in the field for a while, and I like hopping on these shows and get to splice a little bit of machine learning and everything ARM does.
Awesome. And yeah, it's really great to have you here today because it's going to be a really interesting show where we have a lot of machine learning to talk about. So without further ado, shall we introduce our guest then? We've got with us Jason Knight, CPO and co-founder of OctoML. Welcome with us. Hello.
Hey,
happy
thanks.
Thanksgiving.
Thanks so much for having me. Happy Thanksgiving to some of you or all of you as well. And I'm very thankful to be here with three great co-hosts or sponsors. I'm not sure what to call you. Thanks for having me.
Awesome. Welcome. It's good to have you on the show. And thank you again for joining on your holiday. So
it's okay. The cooking is on pause and I just turned the heat off and ran inside here.
Awesome. So I think, as we usually do, I think we want to really give you an opportunity to introduce yourself, but more importantly, to give us some background about your journey to this interesting position that you're in now, right? Like, I think you're leading one of the interesting companies doing a lot of interesting things in the machine learning space. So I'd really be interested in knowing about yourself and how you got to this point. What made you choose this path?
Yeah, sure. I'd love. Happy to. So I guess I can start kind of back in college days. Let me know if you want to go back further. But so I studied biomedical engineering in college, and then kind of stumbled into machine learning world by chance in grad school because I wanted to, get at the heart of kind of complex diseases and diagnostics and therapeutics there. And I joined a grad lab at the time that was applying, as far as I knew, statistics and mathematics, but come to find out it's machine learning to understanding and predicting and controlling biology. Genomic signal processing is what we called it, but essentially machine learning applied to computational biology. And I had a lot of fun there. Built machine learning models myself, kind of built statistical machinery for doing kind of high scale compute on these models and applying that to cancer data and epidemiological data, et cetera. And then fast forward, I graduated and went into the biotech arena and was going to apply this great machine learning to human medical data. And I joined a startup, a pretty big startup at the time, Human Longevity, to apply machine learning to all this data, the world's largest database of human genomes at the time. And come to find out that machine learning just wasn't powerful enough at the time for the kind of data sets that were available, even these massively expensive data sets to collect on tens of thousands of individuals. Biology is just so complex that it doesn't lend its secrets easily to investigation. And so I wanted to get back to closer to the machine learning side of things. I was also doing a lot of data engineering as well, because just handling the massive data sets at that size in AWS requires a lot of machinery, Kubernetes, AWS, et cetera. And so I got to play with a lot of these cool technologies at the time. But I wanted to get back to the machine learning world of things so I could kind of double down on that and then come back and reapply that to biology at a later time in my life. And so I found this startup called Nirvana that is nearby in town here in San Diego, where I'm based. And they were building, or were building at the time, a machine learning accelerator, specifically a deep learning accelerator. So here's a bunch of hardware experts from Qualcomm, Cisco, et cetera. And they had jumped out and started this project to build a deep learning accelerator. At the time, I guess they started around 2015. And it was funny, they were actually really early in the machine learning accelerator game. Like now everyone's building a machine learning accelerator. But at the time they would had lots of stories of going to investors, and the investors were like, what is this machine learning thing? Why do you need an accelerator? Like CPUs, can't you just do it on that? But they were growing quite rapidly, and I joined right before they actually got acquired by Intel, and I actually wanted to do the startup gig with them, and so I was like, rats, I missed my chance, but I'll stick with them anyway. And like I mentioned at the beginning, this is kind of a meandering journey through, but I'm trying to frame it into just story. So hopefully I'm doing a decent job. Anyway, so I joined this team, kind of got sucked into Intel as part of that. And then did a number of things. Worked on the compiler there project. I never done compilers, but just kind of skimmed through some textbooks, and it's all just software at the end of the day, just different flavors of software. And consulted on the cloud division with my kind of experience on the kind of data engineering side as well. And it was a great experience. The team the Nirvana team going to Intel, and then a lot of the people at Intel were just amazing to work with, and just really great. The founding team at Nirvana is a really amazing group to learn from. Amir Khosrowshahi, Naveen Rao, and Arjun Bansal, and now they've all gone and are doing things, exciting things that we can get into. But and so I learned a ton there. And then getting to the OctoML story, I promise I'm getting there. What I saw working, eventually ended up leading the software product group there in the AI products business unit there at Intel that was formed around the Nirvana acquisition. And I saw the enormous amount of energy, time, and money being spent in the software layer on top of machine learning hardware, both existing hardware stacks like CPUs, GPUs, but also new hardware stacks like the accelerators. And the enormous amount of energy and effort being spent there, and how difficult it was, and kind of the gap from where we were, even with all that energy and effort, to where we needed to be in order to serve and cater to the deep learning and machine learning needs of data scientists everywhere. For example, just and what I realized is that part of the problem was the approach that the industry was taking was somewhat backwards. You have tons and tons of very knowledgeable hardware experts at places like Intel, writing handcrafted kernels for these operators in machine learning and accelerating these operators. But it's just a very slow process, and with the pace of innovation in machine learning, it was just not keeping up to speed. And so what that means for end users is you'd have slow experiences and kind of trying the latest and greatest models as opposed to the benchmark models that everyone looks at, Resonant 50, et cetera, and just a number of other problems, but generally just time to market delays and performance problems. And so, but let me pause there and see if there's any questions, because I'm about to get to the kind of next point here, OctoML transition.
May I ask a question real quick? Were you leading into, I mean, on the website, you talk about this compiler approach over kernel libraries towards the end there. Were you kind of leaning towards that? Okay.
Oh, great.
Well, I'm actually excited to hear about that, so I don't have to ask the question. If you're going to be leading into that.
This is where the main character enters stage left of TVM and compilers, because I was at Intel, I was looking at this situation, just like what do you do with to solve this problem, because it's just we're pouring all this energy and effort and money into these handwritten kernel libraries and hooking those up to frameworks like TensorFlow and PyTorch, and it's just not scaling, and it's not even doing the job really we want it to. So what can we do, right? And that's kind of setting the scene there.
So what I find interesting actually is that you started from software, right? Like actually, let's say software. And then you ended up kind of looking really closely at the hardware to then go back at looking at the software and how you can actually, have this kind of layer of how you could reduce the complexity of the end user and simplify the work of the end user by basically creating a compiler effectively, or somewhat of working on a compiler. So it's quite an interesting journey, and I guess it's also interesting that you brought this this idea of working on genome and like bio, right? Because that's to me that's how neural networks and the whole concept of neural network starts, right? And it's interesting that you were actually working in that field before actually then looking at the electronic side, right? And what we do in this world, right?
That's a great point. There's actually a really interesting pattern. Essentially, all three of the founders of Nirvana and many of the employees there actually came from the neuroscience world. And I actually did some work in neuroscience as well, because it's very natural to kind of or study the brain in neuroscience, and then either think, how can I take this knowledge and apply this to the real world? Or kind of slightly different view is well, I can't really understand this unless we build kind of analogs or simulations, and then try and attack the problem through that vector of a system we do understand, and then kind of interrogate and understand that and use that knowledge to then apply back to the brain. So there is a very close relationship between biology and or I would say it's kind of a career trajectory path between neuroscience as a biologist and machine learning as well. It definitely helps to kind of go from the problem domain and applying machine learning to biology, and then kind of going down the stack through software and hardware, and then kind of turning around and turning back up the stack as I go. But interesting point, Alessandro.
I'm going to bring up a comment actually from one of our viewers, Carlo. He says, you can see it down here. This reminds you of something my friend told me. Biology is the closest we have to alien technology, in the sense that it's machinery we haven't built or we didn't invent.
I love that quote. Carlo, great point. And if you haven't studied any biology, I really recommend it, because it's truly humbling to realize how little we understand about it, in the sense that the biology that you study and read in a textbook is a very reductionist approach of, here's an organism and organs and tissues and cells and regulatory networks and genes and DNA, right? And it's this very kind of reductionist approach. And actually, I have a book even that goes into this in more depth. But there are some that argue that this kind of reductionist thinking in biology is actually not sufficient to describe the complexity that exists in biology, because humans kind of engineer things with abstraction boundaries and composability going up the stack, right? In terms of transistors and VLSI and software, or, operating systems and distributed systems, et cetera. And we purposely build those in a way that abstracts complexity. But biology doesn't do that, right? It just kind of throws everything in one complicated milieu of things, vibrating and interacting in random ways. And, one part in a billion works and actually unlocks that. And then that goes and does something else. And it evolves this over billions of years so that all these things are interlocking. And so when you try to untangle parts of the cell and genetic regulatory networks, you realize that, wow, okay, our approach of thinking about things and understanding complexity is not sufficient for really understanding these systems. And so that's actually why I went on this machine learning kind of path, because I don't think human brains are powerful enough to understand biology at the level we need to solve complex diseases like cancer and others. So anyway, that's a whole other tangent, but really, really great topic. Yeah.
And I have a friend. I'll just close this one out here. But I have a friend, a computer science friend from Lenaro. One of his whole things was like, why are we spending all this money and doing all of this stuff out in space when we still don't even understand the stuff that's happening on Earth? Like, we still don't even understand our bodies and all this biology you're talking about. Like, we don't understand anything. And so here we are moving outwards. We should be moving inwards to the molecular level. But yeah. Anyways.
And I don't think we need to do either or. I like doing both. Some people do space, and I'm on the inside, right? The downward track. Okay, well, let me continue then. So before I get too tangented off, but so I had to set the scene here. Is not only Intel was having these problems, right, and just continues to, right? But the entire ecosystem, the entire field, even NVIDIA it was kind of first out the gate with CUDA software stack and their support. Still, has difficulty supporting the just speed of evolution. For instance, tensor cores, which is the kind of ML accelerator, or kind of Juju smart sauce in there. It's not smart sauce. That's a terrible marketing slogan. But the IP innovation that accelerates deep learning workloads. It supports actually on a hardware level Int4, Int2, and Int1 in the newest Turing and Ampere chipsets. But the software side, cuDNN and TensorRT that you use today actually still don't support those out of the box. So as a user, your hardware is supporting all these great features that, because the software layer doesn't support it, you can't get that acceleration. And I'll come back to that with the TVM story. But and so that it wasn't just an Intel problem; it was an entire industry problem. And then I found through random introductions this group out of University of Washington. And Luis Cezes was the PI and professor, and then his researchers, students were building this open source project called TVM. It's not actually an acronym, so it doesn't stand for anything, but you can call it the Tensor Virtual Machine if you want to think of it that way. And it's basically a compiler and runtime, which takes a compiler-based approach to solving this fundamental core problem in machine learning: is how do you make machine learning go fast without needing these low-level experts kind of fiddling with these kernels at a low level. And the way that it does that, because this has been a goal in compilers for decades, right? In the high-performance computing, HPC world, you have people wanting to say, oh, I want to write a kernel or some algorithm to solve PDEs for my space simulation or bridge simulation or weather simulation, whatever. And then I want to write that at a high level and then have that come to compile down to efficient code that runs on one node and 10,000 nodes at the same time. And it's always been a bit of a pipe dream. There's even a meme called the sufficiently smart compiler. That this has been something that the compiler industry has tried to find for decades. But what
Jason,
Yeah, go ahead.
I was gonna pause you for a second.
Yeah, please.
I was gonna say, I love what you're saying, and that kind of backs up the reason for why you're here, right? Because effectively we are super keen to support this effort and get involved in this effort, and as exactly. I mean, we're going to talk about OctoML as well, right? I want to give you a chance to talk about OctoML, yeah. But I think you're part of the ARM AI partner program as well, right?
That's
because it's all about really enabling the ecosystem with all these technologies, and I think actually the compiler technology is a super interesting technology. I mean, we're used to it because we've done in the past, like ARM as a very much a background in hardware, right? And we've done a lot of compilers for our for C code to be compiled to assembly language. Obviously, this is a different problem. I mean, it's a completely different problem, but there are some similarities, and obviously, I personally can really see the power in this approach, right? So I'm really excited for this collaboration and this work. Karl, I wanted to give you a chance to kind of jump in and maybe say a bit more about TVM, our involvement, and also I know that we have someone else waiting to join the show as well.
We do.
Special guest.
Yeah. Yeah, so I think it's a good time, but so ARM is also involved with TVM. As Jason said, like this is a not an Intel problem, not an NVIDIA problem, not an ARM problem, it's an everybody problem, especially from the hardware side. Like since I focus on like the software and the AI, like and the machine learning, I don't want to touch a compiler or kernels and do any of that. So TVM is kind of that nice way that I can focus on my high level languages, which are closer to natural language, and let the machine do the machine interface. So it's super exciting. But yeah, with that one, we should bring in Ramana, who leads our TVM team at ARM.
Hi.
Thank you for joining us today.
No worries. It's freezing outside, but yeah, it's really nice to be back in and talk. Yeah.
Yeah. So I think now is a good time to talk about, I guess, TVM. What does that mean? And then how does OctoML interface with that? And also we should bring up that next week is the TVM conference. So everyone watching should probably go register right now. But yeah, so to learn more about TVM, definitely check out the conference. Both you, Ramana and Jason, you both have presentations there, right?
That's right.
Yes.
That's right.
And Jem Davies, our head of MLG at ARM, will be presenting, I think. So it'll be packed full of good ARM goodness. Plus NVIDIA and Intel is always there, so it's really good. But yeah, if you two could talk about what is TVM, how does it work? And also, like, for me, the thing that took a long time to understand is what is the different about TVM versus an interpreted framework? And like, what does that mean to the end user, I guess, is what we should say.
I can speak to that, Karl. So, for a data scientist today, your typical workflow, you buy a new MacBook or Linux workstation, and you install PyTorch and TensorFlow or one or the other or both, and you're used to kind of constructing models by using that Python interface that TensorFlow or PyTorch gives you, and then executing computations through that framework. Underneath PyTorch and TensorFlow are a set of kernels that are written by engineers at Intel, NVIDIA, et cetera, and those power when you call convolution, conv2D or batch gem or fully connected layer, like those computations call into these libraries of efficient code written by these engineers at Intel and NVIDIA, et cetera, ARM, and that's essentially what drives the compute unit on your computer and gets kind of a high amount of utilization. And then, if you have a sequence of those calls in your model, then those functions are just invoked one after the other, and do the computation for you. And that works great for kind of a large portion of use cases today. The difficulty comes when you start getting into, well, what if I want to do a tweak to a convolution? Maybe I'm a researcher and I want to try a different variant of convolution. Then I want to write a new convolution kernel. Well, how do you do that? If you want to do it with any kind of performance, you need to drop down to the low level, C++, CUDA, or SIMD intrinsic level, and start hacking low level code and worrying about register bank conflicts and L1 cache utilization and hit rates and all of these low-level details that are specific for each architecture and each hardware platform. And even if you're not an ML researcher, these still the problems come to bite you in the sense that each one of these kernels themselves are potentially optimized for your use case, but the combination of multiple of them, there's actually optimizations you can do if you know that you're going to call this kernel and then this kernel by fusing them together. Is a common optimization use case that you can't do unless you have more machinery under the hood to do these kind of things, because these libraries are written in such a way that this kernel runs and then this kernel runs, and there's no way to combine these together except in kind of applying more machinery like you can with a compiler. So that's some of the background there, if that's helpful.
I've got a question, right? Without going into too much details. We don't have a whiteboard here, but I'd really like to. Oh, actually, Karl has one. So maybe Karl, you can write what Jason says. But I'm thinking, can you give us an example of, because I think that's a really interesting thought, right? And something that could really explain where it could make sense to use a compiler, right? So could you give an example of maybe a kernel or an operation more in general that it makes sense to combine with another operation,
right,
and what kind of optimizations you can go for with a compiler and with your
I
technology?
don't think it's going to be visible, but you can just talk through it, I think.
Okay, yeah. I'll talk through it. So a really common one is a convolution kernel followed by an activation or element-wise nonlinearity. And this is an extremely common pattern in all of deep learning. It's actually kind of the core pattern, if you will. And typically the way this is done is, like I mentioned, if you call a convolution kernel and then you call a nonlinearity like tanh or ReLU, then basically the kernel will do that convolution, basically pulling in memory or pulling the data from main memory, doing the compute, and then passing that back out again for convolution. And then it'll get to the nonlinearity. It'll pull that data back in from main memory, do the compute, and then push it back to main memory. And this is very memory bandwidth intensive. And instead, you can fuse these, right? And so for the common operators, ReLU, for example, then NVIDIA engineers and ARM engineers, et cetera, have written fused versions of convolution that say, oh, if you do a convolution, then followed by a ReLU, then actually do the pull from main memory, do the computation of convolution, then do the nonlinearity, and then push that back out all in one. So you save a round trip to main memory. And that's an example of where you can save doing fusion. But then, engineers have done this by work by hand of fusing these kind of operators and enabling some of these fusion opportunities. But then a researcher comes out with a new activation like Swish or ReLU 6 or something like this, and you're kind of just sitting there waiting for NVIDIA or Intel engineers to do update the library to the latest version and enable that fusion opportunity. Whereas the compiler, because it's generating the code for this convolution and this activation at the same time, it can do that fusion for whatever activations you want, and even deeper fusions as well. And you can see how this is a combinatorial problem that compilers just solve naturally by doing the code generation themselves. Whereas an engineer has to kind of okay, I'm going to do ReLU and tanh and maybe like one other and give those opportunities to people through a kernel library. But otherwise, you're just on the hook for what they give you.
Yeah. If you can imagine, I would always walk by this when I was at Intel. There was a cubicle like farm, and it was just all the kernel engineers, and you'd walk by, and I could just imagine like tubes feeding them new operations, and they're like, oh, we have a ReLU, we have to get it optimized, and they just sit there. And then this complicates when you have multiple hardware, because now you have to optimize for this and you have to optimize for this, and then what if someone wants to bring in something new like an accelerator, and it just infinitely goes up in terms of complexity.
Yes, it does. And even within...
Cool. We've got Romana back on.
You're real quiet.
Oh, but there's no audio.
Is the audio much better now, or is it still?
It's not echoing, but we can't hear you.
It's
very
very
much.
quiet.
Yeah.
It's very quiet, which means it's working just slightly.
Maybe while you try to fix that, do you mind if I bring in a question from Carlo on YouTube here? Because I don't want to get too far away from the topic. I mean, we already kind of have, but he's asking, I guess these benefits also apply to frameworks like Fast AI since it's built on top of PyTorch, right? So
yeah, great question. So I mentioned that PyTorch and TensorFlow, 99% of the time work with these kernel libraries under the hood. But actually, compilers like TVM have some level of support for hooking in underneath frameworks like PyTorch, so that you can find blog posts by Facebook and AMD engineers on how to enable PyTorch's TVM mode, where it passes the graph, the kind of computational graph, to TVM to do the compilation, get these benefits, and then execute those kernels rather than the sequence of kernels that are in libraries by vendors, hardware vendors. So yeah, great question.
Awesome. I think let's do what we said we were going to do at the beginning. Actually, give you a chance to introduce OctoML, because I think we talked a lot about TVM, right? But what are you adding? What's your special sauce to the mix, right?
Well, and there's one piece on TVM that I didn't quite cover, which is how TVM is solving this problem when decades of HPC work and compilers has not solved this problem. And there's really two things going on. One is TVM is focused on the machine learning problem, so it's a slightly narrower focus than the generic compilers that exist in LLVM or Clang or GCC. So that helps kind of narrow the problem and reduce the complexity a little bit. But the second innovation is the cool one, which is applying machine learning itself to the process of machine learning compilation. So we actually use in TVM and in OctoML's product, like I'll mention in a second, machine learning in the process to guide the process of code generation to find efficient kernels by learning an online statistical cost model for the hardware that we're tuning for. And I can unpack that, jargon heavy slogans, statements if you want a follow up. But so then this leads to OctoML so TVM's great. I've talked about all these benefits and how you can kind of use it today, but unfortunately, it's still a little bit of a power user's tool in terms of there's a couple of settings you have to set and sharp edges you might hit along the way, and we wanted to make this even easier experience to use so more people could benefit from it. And so that led us to the founding of OctoML and the creation of our first product, the Optimizer, which is essentially a software as a service wrapper around TVM. So all you have to do is just take your trained model once you've finished the training process from whatever training flow you're doing today, and then pass that to us in our API and web UI. And then we optimize and compile that and benchmark that for you, show you the benefits, performance results on a variety of hardware targets, and then allow you to package that up and give that back to you to deploy in whatever downstream application deployment scheme that you're doing today. So that's kind of the elevator pitch of OctoML and the Optimizer that we're, and of course, we're still investing heavily in the TVM ecosystem to continue to drive that and grow that over time, along with partners like ARM as well.
So let me ask you about this. You kind of walked us through that process, right? You have like the easy, fast, portable, getting all of this stuff deployed. That's your process, mm-hmm. right? I'm curious about the statement that you say on the website where you talk about try before you buy. Right. I kind of want to know what that means, right? Because you are referring to hardware, and if you're talking about trying before you buy the hardware, you trying before you buy the service. What is this try before you buy statement, and how does this help developers?
Yeah, a great question. So today, if you want to deploy a machine learning workload to an edge device, let's say a Raspberry Pi, for instance, then first step number one is buy that Raspberry Pi, install it, and then step number N is actually go ahead and install the software, and then take your model and put it there, and then run some benchmarks and see if the performance is anywhere near what you need it to be for your downstream application. Because or almost always you have some kind of latency constraint or throughput constraint that your model has to hit performance X before it's useful in an actual application, because otherwise it's too slow or too inaccurate. Whereas with something like the Optimizer, instead, it's dramatically shortened process of, let me just see. I've been curious about this new hardware over here. Let me just try that. Upload my model to Optimizer. Checkbox the hardware that I'm interested in, and then we'll run it through. Already set up all the software, etc., and then show you the performance both on a baseline like TF Lite, and then also accelerated with TVM compilation. And then you can immediately see, without really investing any work on your own, to kind of try before you buy and see what the performance looks like and if that's acceptable for you.
And are you enabling this hardware? I mean, like, is there hardware that I may want to experiment on that you have not yet enabled? Like, what if I throw out some edge device, the Honeycomb with the Layerscape, NXP Layerscape chipset, and you have not tried that yet? Is this maybe a flag for you to say, oh, we need to get this enabled there? Or, I mean, or is this kind of like working on as many edge devices as possible?
Yeah. So there's kind of two ways that we're approaching that. One is we're obviously a startup and have to start relatively narrow focus. So we have a number of devices today, but there's a little, contact us if you're interested in more, and we're always happy to talk about, setting up more devices for you and your use case. The second is also perhaps even more interesting, which is, and we haven't done this yet, but it's something on a roadmap of enabling you to then download a binary, a small kind of cross-platform binary, and then run that on your device, and that kind of phones home to our infrastructure, and then we can then run execution of processes on your device, and it's all auto updating, etc. And that enables you to that doesn't enable the try before you buy, because that assumes you own the device.
Already bought it.
That would kind of expand our coverage quite a bit. It's kind of the build kite model, if you're familiar with that in the CI world, where you run the agent on your hardware, but it phones home and kind of interacts with the cloud service.
I like that. Yeah, I mean, this brings kind of new utility to things like I'm trying to think of an example, like Mythic Beasts or Mini Nodes, where they host these kind of edge devices. They give you these cloud devices. It's not quite AWS Graviton, but you get access to things like NVIDIA Jetsons and Raspberry Pis, and you can get this stuff tested before you decide to buy it. Very interesting. I like to hear companies doing that kind of stuff. So kudos. That's awesome. Yeah.
Cool. And I wanted to kind of go beyond what you're doing today and really talk about, given your position, your story, how you've got to this point. You've probably seen a lot, right? A lot happening, and you see a lot happening today. Plus, you've got probably the opportunity to work with a lot of partners, and customers are kind of doing different things, different use cases. So I'd really kind of like to get your insights on the trends that you're seeing in the machine learning space from 2 points of views, actually. One is, customer centric, like what are people trying to do that they can't do today, that maybe they will be able to do in the future, but also from a developer perspective, like what is, how is the journey of a developer doing machine learning changing today, especially in the embedded space? I think that's an interesting conversation in its own. So I'll let you.
Yeah, both great questions, Alessandro. So on the customer side, it's been really awesome to see, because there are a number of if you think of the adoption curve of machine learning, there's definitely quite a few still out on the kind of long tail of we're getting our data set up, our data lake's still kind of a data moat instead of a data lake, and difficult to navigate. We're getting our training pipelines set up. We're still kind of deploying these or kind of investigating them in R&D capacity. So that's kind of for an optimist like me a little disheartening, because it's like, oh wow, it's taking the industry a long time to kind of take machine learning and use this in a meaningful capacity. But then there's been also luckily there's been a healthy, really great set of users where they're taking machine learning and not only really seeing benefits of it, but seeing benefits of it and then deploying these out into their main, kind of money makers. And I can't name examples and go into too much detail, but one of my favorites is actually in the biotech world with a Fortune 1000 company of building medical devices, and they have a very healthy business kind of selling these expensive machines that do really amazing things for doctors and clinicians and researchers in the medical space. And they're bread and potatoes, meat and potatoes, money-making machine, they're injecting machine learning straight into the very core of the value proposition of their device and seeing these really enormous gains, and then looking at how to deploy that at a very large scale. And we got to kind of be a part of that from ground zero and see that kind of arise. And that's just a really awesome example of how, you hear the hype of machine learning and how it's, it's doing all these great things for the cloud tech companies, but to see it for a kind of medical device manufacturer and how it's really changing the game and, offering step changes of performance increase for patient and clinician facing, technology. That's been really great to see. And then there's also, of course, the kind of edge side of things, like you mentioned. And actually, I guess this is a mixture of your first and second question. Is now that we're seeing accelerators come online, like the NPUs from ARM, for example, and the kind of various mobile phone handset accelerators like Hexagon from Qualcomm and Bionic from Apple. We're starting to see the kind of shift change from the small amount of compute that was exists in the CPU GPU to the now shift change and kind of the tensor accelerator NPU layer at these new hardware stacks, and you're starting to see, okay, what can we do if we go to the edge and deploy this machine learning model on the edge? And it's still very early days, right? If you look at kind of the maturity or lack thereof of TensorFlow Lite or TensorFlow Lite Micro or even TVM's micro TVM, we're pushing hard on that with ARM, but it's and we're actually giving a workshop at the TVM Conf next Wednesday, so you should free workshop if you're interested in that. But it's still early days, right? We're getting the machinery and infrastructure set up in place, but there's still kind of a lot. Anything in the edge is hard, and machine learning is no exception. But to your question, Alessandro, seeing what's kind of possible when you get to the edge and you don't have these high latencies and high bandwidth costs of transferring data back to the cloud and doing the compute there. We're seeing this a little bit with small examples like Zoom, for instance, in terms of background blur and the smart backgrounds. And these are small examples. Snapchat filters is another one that everyone's familiar with. And these are kind of fun toy examples, but you're starting to see it percolate out. We've talked to several kind of creative media companies that are deploying more and more capabilities on the edge and the creative space. And I think that's where we are seeing it take off first, and kind of the Zoom, Snapchat, et cetera era. But as these capabilities grow, then it builds the infrastructure, and then you start to see more and more on the kind of time sensing and intelligence on the edge. That because I think we're all used to just microcontroller powered devices and kind of how simplistic they are, but as they start adapting to you and learning your patterns and behaviors, and then kind of predicting that and preempting you and suggesting things, like these are really what's exciting on the edge that I've seen from talking to customers.
Yeah, I'm also really excited about that. The last year or two has been big in terms of, now we've been doing, it's kind of democratizing AI and machine learning, and now you don't need a cloud connection, you don't even need an internet connection, but you can still build machine learning models and run them and interact with them, and it's getting easier. And TVM is the next thing, I think, that's going to make it even easier for more people to get used to it, because now that bridge between research and being able to deploy things is getting smaller and easier to cross, I think, because if you can imagine something, it's going to be a lot easier.
Yeah, one to kind of up level this a little bit is even further, I guess I should say, is I have kind of a far out there prediction that that more people will be training and fine tuning machine learning models than are writing software today in a very short amount of time. And at first that might sound crazy, because it's like, well, wait, machine learning is even harder than writing software because it's this layer on top of software. But when you look at actually what machine learning enables, it enables you to train computers to do tasks that are interesting to you by giving it feedback, yes, no answers or reward signals when it does the thing you want. And this is a very natural human behavior. Like we're used to doing this all the time with humans and children and dogs and cats and pets. And so as we get the right interfaces to tell the computer, no, that was the bad choice. You did the wrong thing there. Or good job, computer. That was the right thing. Keep doing more of that. Then everyone will be training machine learning models in some capacity. And as more and more devices get that capability, then it's going to kind of percolate and enhance every aspect of our daily life. So that's what I'm excited about enabling through kind of the deep tech of OctoML and TVM, along with ARM and partners.
Yeah, I think that's a great point. That's really why I got into machine learning to begin with. Like, it's not because I like programming. I hate programming. I want the computer to do that part, and I just get the cool results and the good job. I'm like, yeah, you did it. Good, sweet. I can go do other things.
Actually, Karl, your point reminds me. The first time I actually trained a deep learning model, I was actually applying it to a really awesome protein data set that was tens of millions of protein sequences, and then their kind of functional capabilities and whether they embed in the membrane layer in the cell wall, or whether they're active in protein express or protein activation or whatever. And I was so excited to apply this new deep learning that I had heard about, and I remember kind of pulling out TensorFlow at the time and running my multi-layered ConvNet and then training that overnight, and then coming back the next day and seeing great results, and that was exciting. But then kind of the day after day went on, and I was like, wow, this is actually it's pretty repetitive process of kind of, there's not a lot of science behind what layers go where in the deep learning model, and it's very heuristic of, well, I guess I'll try maybe a conv layer here with depth this, and I'll just do a parameter sweep and try a few different things. And I was like, pretty quickly, I was like, wow, this is something a computer should be doing for me, right?
Yeah. It's very much a Bob Ross approach to, well, let's just put a little convolution layer here and a little happy ReLU here, and it'll work. And then it comes out, and you're like, oh, there's no mistakes. It's all fine. It just comes out in the end.
That's super interesting though, because I was actually in a conversation the other day on compilers, not ML compilers, but compilers, right? And actually, it's interesting because you have basically, if you talk about exactly what you just said now, like there is a lot of heuristic that goes into deciding what you're building, right? Like how you should write what you've got in mind at a higher level. Something that you're describing at higher level language, how to compile that to something lower down, right? And there's a lot of heuristic that goes into doing that. But at the same time, if you want to do it, if you want a machine to do it, you have to tell it how to do it, or you have to get it to learn how to do it, right? So I'm really curious to know the approach that, what's the most interesting approach to you to get that logic into the machine, right? Because effectively, you have to put the logic into the machine to get that compiler to do the things that a human would do. And how do you go about that? And what is the best approach there?
Oh man, there's a lot of questions. So one thing is I've been talking mainly about the compiler and the kind of deployment side of Pain, but we started switching into the training side of Pain, which is interesting. So one of the things that's interesting there is that I wanted to touch on was declarative training. And so this is where, instead of you explicitly saying, here's my model, and Bob Ross, I like that analogy, Karl, of kind of happy little cloud over here, and maybe a conv 2D layer with depth of 64 here, and maybe a ResNet skip connection over here. Instead, declarative training, which is popularized by, I guess the most popular example is the Ludwig project out of Uber originally, is you describe your data set in declarative, I think it's YAML actually, even. Not that we don't have enough YAML already, but coming from the cloud world, I have some scars from my battles with YAML. But anyway, so you describe your data set in terms of like what the input format is, shapes and data types, et cetera, and then what the desired output looks like. And then you essentially hand that to a system that then tries out a different set of models for you. And so it automates the kind of happy conv layers and tries out a few different variations. And this is similar to something called network architecture search, which is something you might have heard of in the literature if you follow this space, where you take a Google size compute cluster and you try thousands of different parameters and you try all different connections. But this is kind of the dumb NAS version where it's just you try a few different kind of baked in parameter sets, and actually the results are quite good, and they're using this at Apple. Chris Ray gave a great talk. He's a professor at Stanford and also works inside of Apple, and they've been using this to great effect in many of their kind of internal processes. And unfortunately, that recording is not up, but you can see some of his work in the Overton project, I think is what they call it, and Ludwig itself. So I guess I'll stop there. There was one other thought I had with your question, Alessandro. Objective functions. Yeah, I'll come back to that. The difficulty.
Cool. No, that's interesting, because I think I think it's about like getting the machine to do the work for you, but you have to tell it. You have to find a clever way to get it to do it, right? And
that's right.
And I guess the approaches that you were talking about are definitely interesting, but they do require a lot of compute, right? How do you, I guess, is there ways that allow you to do less compute to actually get to a good result, right? Like what is the path there?
Yeah, one nice thing there is that yes, these approaches cost more compute, but surprisingly, unsurprisingly, I guess the typically almost always the more expensive factor is your own time and engineering time rather than compute costs. And part of that is just kind of an extension of, maybe not Moore's law, but whatever kind of TSMC scaling law we're on these days, in terms of, companies like ARM are going to keep giving you more and more compute over time. And so as long as you can leverage that, right, with something like a compiler and TVM, then the more important thing is to think, okay, in a year's time, 2 years' time, how can I reduce my time and leverage the compute time that's available with the increasing amount of both cloud and edge computing available. And so another example of this is Once for All Networks out of Song Han's lab at MIT is one of my favorite things in my kind of Christmas favorite things list. There's Declarative Training and Ludwig, and then there's also this Once for All project from Song Han's lab. This is where, so another problem on the edge is that you've got a huge variety of devices that you need to deploy to. And so, especially in the mobile realm and Android, you have, 5-year-old, $50 phones all the way up to brand new, $1,200 phones. And so how do you train one model and get, good accuracy and performance across all those devices? And so Song Han's Once for All project, and I forget the first author on that, but was basically you train one model that's about 10 times larger than a normal model, but instead of kind of having a single model that is a result of that training process, you train it in such a way that you get a combinatorially large number of valid models that you can extract out of that single model that you train. So basically, you can take the small model here, the medium-sized model here, and the large model here, and I think it's on the order of 1,000 or 10,000 models that you can extract out of a single model. And each one of these submodels is pretty good at the task you trained the entire thing on. But it gives you a lot of choices of accuracy and performance trade-off. So you can extract out a bunch of these models out and for kind of different buckets of performance tiers, and then kind of go out and give those to the various devices depending on how much compute's available. So that's another way you can trade off compute versus kind of engineering time on your side.
We got a comment from the audience. I shot JR saying machines can do the work. I guess it's a quote from IBM 1967. So it seems like it's it's something that's been going on for a while. But I think it's super interesting to hear. You're working on this day in and day out, right? So it's interesting to hear your thoughts on how things are evolving and what's happening and where we're going. Because I think I definitely see more of this coming, right? And there's going to be, as you said, there's going to be more compute available. So there's going to be more people taking advantage of that compute in different ways. And I think this is a really clever way to take advantage of compute by basically finding the best network that you can run and the best way to run it actually on the specific device, right? And actually, you mentioned about the diversity in client devices, but actually even in the IoT space, it's even more of a diverse system or set of requirements in hardware. So I think stuff like this is super interesting.
Another analogy too to apply is kind of historical analogs. Is machine learning is in the phase that general purpose computing was in the depending on where you're looking, anywhere from maybe late 70s to early 90s, in that the various latest and greatest model architecture that comes out, ResNet, 50 or ResNext or EfficientNet or BERT, or Electra, or all of these variations are basically kind of better B trees or better hash maps, right? Like, when's the last time you worried? Well, if you're a geek and you love learning about this stuff, maybe you've learned about various types of hash maps and B trees and dug into that side of things, but most people just take whatever hash map or B tree library their standard library gives them and is happy enough with that, because over decades of optimization work, those have been optimized, and you kind of just don't care about the abstraction underneath. Whereas in machine learning, we're still at that low level data structure, fine tuning and performance knob. So we don't know what the set of kind of B tree map for this use case, hash map for this use case, this sort algorithm for these kind of data sets, and so that's where machine learning is. And so the whole goal is to really build the tooling and infrastructure and knowledge so that we can level up the abstraction and then start building more and more applications more easily, as we do in normal computer science. Like, if you had to write your own custom B tree and hash map and TCP stack for every time you wrote a new application today, like, no wonder things wouldn't get done. And that's where we are in machine learning today. You see these great results where people can kind of write their entire stack from B tree on up, equivalently in the machine learning world. But it's more rare than as it was, when they would have to do that for the game that they were building, Pong or whatever. Then they had to do all the low level details themselves. So that's one analogy I like to apply on the field today.
Definitely, no, it's definitely interesting. I think as you mentioned, with all this new compute available to everyone, I think we're gonna scale quickly, right? And we're gonna see more and more of automated work being done by machines, right? So I think this is super interesting, and I'm conscious that we hit the hour. So I really wanted to give you a chance to do a kind of shameless plug and talk about maybe tell people where they can find more about OctoML and potentially what's interesting to check out.
Sure. Yeah, I'll I guess actually, can I share my screen here? Let's see. I think this is working. So yeah, let me know if you can see this, right? This is our website, octoml.ai. We are actually launching, we'll have some news at the TVM conference next week about our product, the Optimizer, but feel free to sign up here if you're interested in learning more and being part of the early access program. I have actually, I can just kind of tease some shots of what the Optimizer looks like. Here's what it looks like when you upload a model, and it's quite simple. And then once you upload a model, you can select various hardware types to run on and benchmark against, and then download packages from. But it's just designed to be a sneak peek there. And then definitely check out the TVM Conf website. That we'll be posting a link to, but it's tvmconf.org, and feel free to register. It's a free registration. Check out the schedule down here. Talks from Qualcomm, MediaTek, Berkeley, ARM, etc., Amazon, and the TVM website itself. Definitely check this out. And also, contributions in most part by ARM. Check out the TVMC binary. And so this is a nice command line way you can use TVM today to tune, compile, and run and benchmark models on your own hardware for free, and using just open source TVM software today. So that's just a number of links I wanted to share, but other than that, I'll stop sharing. And thanks for the opportunity.
Awesome. And I mean, if you want, I can also plug in your Twitter account. I don't know if you want to share that.
Oh, sure. Yeah, I'll
yeah. So I've got it up here. So go follow Jason on Twitter. We've got the Twitter down here.
Oh, and also OctoML too. But yeah.
OctoML as well. Yes. So awesome. I mean, really cool to have you on the show. And I think, we've kind of opened a kind of worm, I feel, right? I feel like there's so much more to talk about here. But, this was just more of a teaser, because actually, yeah, you're going to do a talk next week, and there's going to be a lot of interesting things coming up next week. So Karl, do you want to kind of close on TVM, perhaps, the conference next week? And perhaps, I mean, we've already shared the website here, but I'll share it again. If you want to add anything else.
Yeah, definitely. If you're interested in TVM, you should be. So check out the conference. It's a good way to learn it. I went last year, and that was kind of my first introduction. It's a really good community that's kind of growing quickly, and now is a good time to get into it as it's growing and gaining adoption and getting easier to use. So I would definitely check it out. It's kind of that next wave of machine learning compilation tools. So if you're in machine learning, it's good to at least be aware of. Awesome.
And we've got, Jason here right at the center of that ecosystem. So it's going to be exciting to see what comes out of this collaboration. I'm excited to, watch next week and see, try out the OctoMizer. Is that
That's
right?
The name.
OctoMizer.
Yeah.
But no, thank you so much for being with us today. And, even though it's your holiday, but thank you so much for joining us, and really appreciated the time. And I had a lot of fun. It was a lot of things to learn for me, because I'm not an expert in when it comes to TVM and to compilers. So that was really cool. Thank you.
Great. Well, thanks for having me. And it was great to have the chance to talk about some of this stuff. And now I can go start cooking again. No problem.
Thank you for your time, Jason.
Thanks, Robert. Thanks, Alessandro. Nice to meet you as well. And good to see you again, Karl.
Yeah, good to see you. I'll see you next week at the conference, I think. However much you interface virtually at a virtual event.
We have something, so stay tuned. Gather.town.
Oh, sweet. That'll be great.
Yeah. Awesome. Well, if you share it with us, we can share it on the links below, because we'll be putting the links below this video. So everything that we talked about today is going to be linked underneath the video. So stay tuned for that. And again, thank you everyone for joining in today. Hope you had fun as much as I did, and see you next week. Bye, everyone.
Bye, everyone.
Bye.
Thank you. Bye.